Course title: Geology. Paper title: Economic Geology and Mineral Resources of India. Topic of the lesson: ore deposits associated with intermediate to felsic igneous rocks. Part 1: Orthomagmatic iron deposits and pegmatites. Objectives: to understand the mode of occurrence of orthomagmatic iron deposits associated with intermediate to felsic volcanic rocks. The mode of occurrence of pegmatites, their mineral wealth, depth-wise classification of pegmatites, and diverse views on their origin. Orthomagmatic deposits. Felsic magmatic melts are rarely in a position to generate significant ore deposits during orthomagmatic stage, but iron, mainly magnetite, with or without apatite, deposits encountered at several locations are considered as of magmatic segregation origin. This hypothesis was put forward by Williams, 1969, in view of the interesting occurrences of undoubted magnetite, hematite, apatite lava flows in Chile, Park, 1961. The magnetite deposits occur both as lava flows and dike-like bodies. Major occurrences are encountered at Kiruna and Gällivare, northern Sweden, Savage River, Tasmania, Baf District, Iran, Larope, Philippine Islands, Korshunsk in Irkutsk, Russia, Iron Mountain in Missouri, USA, Cerro Mercado and Durango, Mexico, and Chilean Iron Belt, Chile. Chilean Iron Belt is 600 kilometers long and 25 kilometers wide and consists of number of magnetite deposits. Prominent ones are located at Pluto Melon Ore District, Magnetita Pedernales, and El Laco. The above listed deposits occur in volcanic or volcano-sedimentary terrain, but there is no suggestion of some correlation of deposit type with specific volcanic rock type. This is because of Savage River occurrence with metamorphosed tholeiitic basalts, Iron Mountain with andesites, and the Baf District, Iran, and Cerro de Mercado, Mexico, with rhyolites. The Kiruna District, Sweden, contains several magnetite deposits, the largest of which is Kirunavara, Figure 1. The Kirunavara ore body crops out over a strike length of 4 kilometers, extends down dip for at least 1 kilometer, and is 80 to 90 meters thick. In the Kiruna district, the stratiform and concordant nature of the magnetite ore bodies and their volcanic setting are apparent. The ore bodies at Kirunavara and Luosvara are sandwiched between foot-wall keratophyre and hanging wall quartz keratophyre, Figure 1. The ores are both massive in part and well banded elsewhere. The banding can be attributed to flow banding. The ore body at places consists of columnar and dendritic magnetite. The columnar magnetite compares well with that from El Laco flow, Chile. The dendritic magnetite texture is similar to the skeletal platy olivines in the spinifex texture of comatite. The ore consists of fine-grained magnetite or more rarely hematite and contains variable amounts of fluoropatite. After apatite, actinolite and diopside are the most abundant non-metallic minerals. Average iron content in apatite poor ore is 67% and apatite-rich ore is 2 to 5%, phosphorus is 60%. A number of workers have suggested that the concordant magnetite deposits of Kiruna district are oxide lava flows. The Pleito Melon district, Chile, contains several small deposits and numerous magnetite dikes. A volcanic sequence, andesite lavas with interlayered rhyolitic tuff and breccias, and an intrusive complex tonalite, granodiorite, and diorite constitute the country rock. Ore bodies are stratiform, flow-like, and pyroclastic. Breccia, dikes, and stockworks made up of magnetite with minor amounts of apatite, jarosite, and amorphous silica. The limited lateral extent of magnetite ore bodies with repeated vertical transition from dense to vesicular ores, signifying tops of individual flows, columnar, magnetite indicating rapid growth, vesicle trails revealing fluage folds in small scale, magnetite octahedral and porous interstices constituting the bulk ore, occurrence of lens-shaped lapilli and ash bands within magnetite flow. The presence of magnetite apatite ash just beneath the magnetite lava and presence of magnetite with or without actinolite apatite, dikes with pegmatoidal grain size all point to a lava flow origin. Travisani et al. 1995. At El Laco of Chilean Iron Belt, 5 main ore bodies comprising magnetite lava flows associated with secondary craters occur around a central rhyodacite plug. The stratovolcanic sequence at El Laco began with andesite flows, followed by the rhyodacite plug and ignimbrites, and culminated in the extrusion of magnetite lava flows through secondary craters. The magnetite apatite melt, now representing oxide lava flows, were generated possibly during magmatic differentiation as immiscible fraction within the parent magma. Separation of the two immiscible fractions took place possibly deep within the Earth's crust prior to intrusion. There exists another view with regard to the origin of magnetite with or without apatite deposits based on specific evidences found in Kiruna district, Sweden, and El Laco, Chile. At Luossavaara, what appears to be stockwork feeder channels underlies the ore body, and the hanging wall breccia consists of ore fragments which possibly indicate explosive volcanic activity. At El Laco, the footwall andesite has been subjected to alteration by augite, scapolite, albite, orthoclase, calcite, magnetite, apatite, metasomatism. Oresks et al. 1994. These data are provided as evidences for hydrothermal mode of origin, Bookstorm 1995. Park 1985 suggests that the magnetite deposits of Kirunavara are of exhalative hydrothermal origin. Solomon 1976 considered these deposits as an end member of a range of ore types from massive sulfide over 90% iron sulfides, deposits containing minor magnetite through magnetite pyrite ores with minor chalcopyrite such as Savage River magnetite ore, Tasmania, to stratiform iron oxide ore such as the one at Kiruna district, Sweden. At present, magnetite with or without hematite, apatite deposits account for 2 to 3% of the world's iron ore production. Pegmatites and their mineral deposits. Introduction. Pegmatites are coarse-grained igneous or metamorphic rocks, generally of granitic composition. Pegmatites of granulite and some amphibolite facies terrains are frequently indistinguishable mineralogically from the migmatitic leucosomes associated with them. Pegmatites developed at higher structural levels and often spatially related to late tectonic granite plutons are often marked by minerals with volatile components, hydroxide, fluorine, boron, and a wide range of accessory minerals containing rare lithophile elements. These include beryllium, lithium, tin, tungsten, rubidium, cesium, niobium, tantalum, rare earth elements, and uranium. Chemically, the bulk composition of most pegmatites is close to that of granite, but components such as lithium oxide, rubidium oxide, barium oxide, fluorine, and rarely cesium oxide may range up to or just over 1%. Pegmatites are mined mainly for tin, niobium, tantalum, rare earth elements, yttrium, zircon, beryllium, and uranium ores. Gem quality beryl, emeralds, aquamarine, morganite, goshenite, chrysoberyl, cat's eye, alexandrite, topaz tourmaline, optical grade fluorite crystals, piezoelectric quartz crystals. Feldspars required for the ceramic industry. Lithium minerals, spodumene, petalite, lipidolite for the glass industry, fluxing of aluminum reduction cells, and manufacture of lithium compounds. Book mica, muscovite for the electrical industry, electronic tubes. Pegmatites constitute virtually the only source of sheet mica, K feldspar for porcelain ceramics and piezoelectric quartz crystals, and had been the only source of lithium, beryllium, rare earth elements, niobium, cesium, rubidium, tantalum, niobium ores until modern efficient mining and processing technologies made it possible to extract lithium from brines produced in USA, Chile, and Japan, beryllium from hydrothermal mineral bertrandite, rare earth elements and niobium from carbonatites, lithium, cesium, rubidium, beryllium from volcanoclastics, and niobium tantalum from tin slags. Smelting of tin ores in Thailand gave rise to slags containing about 12% tantalum oxide. Although pegmatites are widespread in space and time, some belts and fields are particularly well known for their huge resources and giant crystals. Example, 12-meter long spodumene crystals in Black Hills Pegmatite, USA. Feldspar single crystals weighing more than 1,000 tons in Karelian Pegmatite Belt, Russia, and or multiple ores and industrial mineral content. The Black Hills in South Dakota, USA, the Karelian Belt in Russia, the complex zone Bikita Pegmatite in Zimbabwe, the Bancroft Belt of polymetallic pegmatites in Ontario, Canada, the uraniferous Rossing pegmatites in Namibia, the world's largest single producer of uranium ore. Large pegmatitic lithium resources in Zaire and France, tantalum-bearing Greenbushes pegmatite, Western Australia. 450 kilometers long and 20 to 70 kilometers wide pegmatite belt in the Mongolian Altai merits special mention. Indian occurrences of productive pegmatites lie in several regions. The Bihar pegmatite belt incorporating Hazaribagh, Munger and Gaya districts. The Nellore belt in Andhra Pradesh comprising Srikakulam, Nellore and Vishakhapatnam districts, and the Bilwara, Ajmer, Jaipur, Udaipur districts in Rajasthan belt. All the Indian occurrences are predominantly mica pegmatites with beryl, emerald in Ajmer and Udaipur, and some niobium tantalum minerals as co-products. Cassiterite-bearing complexly zoned pegmatites occur in the Koraput, Orissa and adjoining Bastar, Chhattisgarh districts, and in Palanpur and Banaskantha districts in Gujarat. All these occurrences are confined to the Precambrian shield areas. Simple and complex pegmatites. Pegmatite bodies vary greatly in size and shape. They range from pegmatitic schillerin and patches in parent granites through thick dikes many kilometers long and away from any possible parent intrusion to pegmatitic plutons. They form simple to complicated fracture-filling bodies in competent country rocks or elliptical lenticular bodies in incompetent hosts. Pegmatites are often classified as simple or complex. Simple pegmatites have simple mineralogy and no well-developed internal zoning, while complex pegmatites may have a complex mineralogy with many rare minerals. Example, pollucite, amblygonite, but their distinct feature is the arrangement of their minerals in a zonal sequence from the contact inwards, figure 2. An example of complex zoned pegmatite from Zimbabwe is given in figure 3 and table 1. The main pegmatite body at Bikita, Zimbabwe is 2 kilometers long, 45 to 60 meters thick, and contains, among others, lepidolite, spodumene, petalite, pollucite, beryl, eucryptite, and amblygonite, cassiterite, tantalite, and microlite. Complex pegmatites display internal zoning that may be purely textural with fine-grained border and coarse-grained central part, or purely mineralogical with plagioclase, K-feldspar, biotite along the margin, and albite with or without rare minerals, core and a quartz-bearing intermediate zone. Occasionally, zoning is a combined textural mineralogical feature. It is almost universally established that the inner zone materials produce tongue apophysis or cross-cutting veins into the outer zone, but never the other way round, figure 4. This implies a core word Younging pegmatitic sequence. The pattern is broadly consistent and recurrent both in space and time. From the Black Hills, USA, pegmatite belt, 12 sequentially developed assemblages have been documented from more than 100 pegmatite bodies. Depth-wise classification of pegmatites. Pegmatites have been classified in several ways using as many as 9 major criteria: morphology, the inferred pressure-temperature regime of their emplacement, their mineralogical and chemical composition, internal structures including compositional and grain size zoning, etc. Binsberg et al. 1979 and Cerny 1989 provided the following simple four-fold depth-wise classification of pegmatite formations. Number 1. Pegmatite formation of shallow depths myorrolitic cavity pegmatites 1.5 to 3.5 kilometers, pegmatite pods in the upper parts of epizonal granites. Cavities may supply piezoelectric quartz, optical fluorite, and gemstones. Number 2. Pegmatite formation of great depths, mica-bearing pegmatites 7 to 8 to 10 to 11 kilometers, only minor rare metal mineralization emplaced in intermediate pressure Berrovian series, upper amphibolite facies metamorphites, largely the products of anataxis. Number 3. Pegmatite formation of intermediate depths rare metal pegmatites 3.5 to 7 kilometers, filling fractures in and around possible parent granites or quite isolated from intrusive granites, emplaced in low pressure Abukuma series, amphibolite facies metamorphites, mainly or wholly magmatic differentiates. Number 4. Pegmatite formation of maximal depth more than 11 kilometers and granulite facies terrains, usually no mineralization, commonly grade into migmatites. Depths shown in the above classification are very much on the shallow side. Genetic aspects. Pegmatites may occur singly or in swarms, forming pegmatite fields, and these in turn may be strung out in a linear fashion to form pegmatite belts. For example, pegmatite belt of Mongolia contains over 20 pegmatite fields. Pegmatite in a particular field may show a regional mineralogical or chemical zonation. When a swarm of pegmatites is associated with the parent granite pluton, the more highly fractionated pegmatites enriched in rare metals and volatile components are found at greater distances form the pluton. The degree of internal zoning also increases with an increase in rare metals and volatiles. In terms of their settings, the bulk of pegmatites occur in orogenic belts that are mostly cratonized at later stages. These are related to both syn-orogenic and post-orogenic granitoids, the latter variety being more productive. A minor group termed anorogenic pegmatites are related to intrusives connected with rift grabens or fault systems. Pegmatites are considered as forceful intrusions that postdate the peak of regional metamorphism and granite emplacement, and majority of granites are leucocratic alkali granites that display heterogeneity ranging from biotite granite at depths to 2 mica and muscovite garnet facies in their cupolas. Some 80% of the world's metalliferous pegmatites, are of Precambrian age. Most pegmatites, whether igneous or metamorphic in origin, have similar bulk compositions, and these correspond closely to low temperature melts near the minima of albite, anortite, orthoclase, quartz, water systems. These melts are developed by extreme magmatic differentiation or anatexis. Many rare metal pegmatites appear to be of magmatic origin. Their unusual composition appears to be a consequence of retrograde boiling and the manner in which elements are partitioned between crystals, melt and volatile phases during the cooling of the magma. Bonding factors such as ionic size and charge largely prevent many constituents, volatiles and lithophile elements, originally present in minor or trace concentrations in the magma from being incorporated into precipitating crystals. As a consequence, they become highly concentrated into the residual melt. In the case of granite, it is also enriched in water since quartz and feldspars are anhydrous minerals. The list of residual elements is long but includes lithium, beryllium, boron, carbon, phosphorus, fluorine, niobium and tantalum. In pegmatites, tin and tungsten minerals are of orthomagmatic origin. In vein deposits, titanium and tantalum minerals are of hydrothermal origin. A steady increase in water content as anhydrous phases are precipitated will also mark the crystallization of pegmatitic melts, and a point may be reached where retrograde boiling produces a water-rich phase. Sodium, potassium, silicon, and some other residual elements listed above will be fractionated from the melt into the water-rich phase, within which atoms can diffuse much more rapidly than in a condensed silicate melt. Consequently, rates of crystal growth are greatly enhanced, and this may have an important bearing on the growth of giant crystals in pegmatites. Further, different pressures give rise to the crystallization of different phases. For example, primary lithium aluminosilicate phase crystallizes either as spodumene or petalite depending on pressure. Broadly speaking, 5 hypotheses have been put forward to account for the development of internal zoning. Number 1, fractional crystallization under non-equilibrium conditions leading to a steady change in the composition of the melt with time. Number 2, deposition along open channels from solutions of changing composition. Number 3, two-stage model. A. Crystallization of a simple pegmatite with B. Partial or complete replacement of the pegmatite as hot aqueous solutions pass through it. Number 4, three-stage evolution during magmatic subsolidus hydrothermal evolution, beginning with the magmatic melt stage through an immiscible melt fluid stage, eventually to a dominantly fluid stage. Number 5, hybridization through assimilation of or reaction with country rocks. At the present time, most investigators prefer the first or the third hypothesis as the majority of the evidences, such as complete enclosure in many pegmatites of the interior zones, do not favor the existence of open channels during crystallization. As the third theory encounters difficulties in explaining the worldwide similarity of internal sequences, the first theory finds most favor. The concept that the internal evolution of zoned granitic pegmatite resulted from the crystallization of water-saturated melts that evolved to produce systems with a melt and a separate aqueous fluid finds support from the studies of Thomas et al. 1988 on Tango pegmatite, southern Manitoba, USA. They traced the thermal evolution of this pegmatite from the initial intrusion of a mixture of an aluminosilicate melt plus and water carbon dioxide dissolved salt fluid at 720 degrees centigrade to final crystallization of quartz zone at 262 degrees centigrade. Initial crystallization was from the wall rock inwards, with the wall zone crystallization commencing at about 600 degrees centigrade and the intermediate zone temperatures being around 475 degrees centigrade. The fourth theory was inferred by Lu and Zhon Wang, 1994, from their studies on pegmatite of Xinjiang province, China, confined to a gabbro overlying a biotite granite. The pegmatite body, largest known pegmatite body in China, is mined for lithium, beryllium, niobium, tantalum in spodumene, beryl, and pollucite. The pegmatite body comprises 10 zones, each characterized by distinctive mineral assemblages, melt fluid inclusions of specific ranges of composition, salinity and temperature, and inwardly younging paragenesis. Fluid inclusions in minerals, quartz, spodumene, beryl, patellite, in different zones indicate the following temperatures of homogenization and salinity. Zone 1, 700 to 900 degrees centigrade melt and 570 to 720 degrees centigrade melt fluid. Zone 3, 570 to 720 degrees centigrade melt fluid. Zones 6, 7, 8, 9 and 10, 305 to 510 degrees centigrade, aqueous and water carbon dioxide. Fifth hypothesis finds support from field evidences provided by several major pegmatite occurrences. In many studies, it was found that the nature of mineralization within the pegmatite had a decisive control of the immediate host rock. In the Bancroft Field, Ontario, uraniferous granitic pegmatite dikes are mostly conformable with the metamorphosed host rock gneiss figure 5. The ore bodies occur at the footwall or hanging wall contacts but sometimes occupy the entire pegmatite. The pegmatites have a metamorphic fabric, contain non-rotated enclaves, and show a tendency for their lithology to be governed by changes in the nature of their host rocks. The principal uranium minerals are uraninite and uranothorite. Average ore grade little above 0.1% U3O8, and the mineralization is best developed where the pegmatites cross a zone containing graphitic pellitic gneiss. This association may indicate that the ultimate source of much of the uranium is to be found in these altered black shales. A situation similar to the above prevails in the Rossing uranium deposits, world's largest uranium producer, Namibia, figure 6. The uranium mineralization occurs within a migmatite zone and is characterized by largely concordant relationships between uraniferous pegmatitic granites, alaskites, and the country rocks. The region witnessed upper amphibolite facies metamorphism based on the presence of cordierite in the pellitic gneiss, indicating a Bukama-type metamorphism. Economic uranium mineralization is concentrated where the pegmatites are emplaced in certain metasedimentary zones, including pellitic gneiss. Burning et al. 1976 favored an initial distribution of uranium within the metasedimentary sequence and its later concentration in anatectic melts of alaskitic composition, which shows only minor evidence of movement from its zone of generation. Cassiterite with lepidolite, beryl, spodumene, bearing zone pegmatite at Govindapal and other places in the Bastar Koraput area, India, are best mineralized when completely enclosed within metabasic rocks. The mica belt of Bihar, India, shows prolific development of high-grade mica books only where the pegmatites are in contact with mica schists. The above examples underscore the importance of assimilative enrichment of pegmatites through reaction with the country rock. Summing up, the origin of simple pegmatites is now better understood, while the origin of zoned complex metal-bearing pegmatites remains controversial and far less constrained. It is possible that diverse mechanisms operate in their genesis, and at least in some instances, the elements are derived from the host rock. Summary 1. Orthomagmatic deposits associated with felsic volcanism. Felsic magmatic melts are rarely in a position to generate significant orthomagmatic deposits, but iron deposits consisting of magnetite with or without apatite encountered at several places are considered as of magmatic segregation origin. These deposits occur both as lava flows and dike-like bodies. Major occurrences of iron deposits of the above category are encountered at Kiruna and Gällivare, northern Sweden, Savage River, Tasmania, Baf district, Iran, Korshanovsk in Irkutsk, Russia, Larab, Philippines, Iron Mountain in Missouri, USA, Cerro Mercado and Durango, Mexico, and Chilean Iron Belt, Chile. Genesis of felsic magma-associated iron deposits is controversial. Travisani et al. 1995. Assign orthomagmatic origin for these deposits based on the following features noticed in them. 1. Limited lateral extension of ore bodies with repeated vertical transition from dense to vesicular ores, signifying tops of individual flows. 2. Columnar magnetite bodies indicating rapid growth. 3. Vesicle trails revealing flowage folds in small scale. 4. Octahedral magnetite and porous interstices constituting the bulk ore. 5. Occurrence of lens-shaped lapilli and ash bands within magnetite beds. 6. Presence of magnetite apatite ash just beneath the magnetite lava. And 7. Presence of magnetite with or without actinolite apatite dikes with pegmatoidal grain size. There exists another view based on specific evidences found in Kiruna district, Sweden, and El Laco, Chile, which include a. Stockwork like feeder channels underlying the iron ore body. B. Presence of iron ore fragments in the hanging wall breccia, possibly indicating explosive volcanic activity at Luozzavara, Kiruna district, metasomatic alteration of footwall andesite, and El Laco, Chile. These features, according to Bookstorm 1995, are evidences for hydrothermal mode of origin. Earlier, Park 1985 suggested an exhalative hydrothermal origin for Kirunavara deposits, and Solomon 1976 suggested that iron deposits are an end member of a range of ore deposits of massive sulfide deposits. 2. Pegmatite deposits. Pegmatites and their mineral deposits. Pegmatites are coarse-grained igneous or metamorphic rocks, generally of granitic composition. Pegmatite developed at higher structural levels and often spatially related to intrusive late tectonic granitic plutons, are often marked by minerals with volatile components and a whole range of accessory minerals containing rare lithophile elements including beryllium, lithium, tin, tungsten, rubidium, cesium, niobium, tantalum, rare earth elements, and uranium. Pegmatites are mined for a. tin, niobium, tantalum, rare earth elements, yttrium, zircon, beryllium, and uranium ores. B. Gem quality beryl, chrysoberyl, topaz, and tourmaline, optical grade fluorite crystals, piezoelectric quartz crystals. C. Feldspar required for ceramic industry. D. Lithium minerals, spodumene, petalite, lepidolite for the glass industry and manufacture of lithium compounds. E. Book mica, muscovite for the electrical industry and electronic tubes. Major and economically significant pegmatite occurrences are encountered at the Black Hills in South Dakota, USA, the Karelian Belt in Russia, the complex zone pegmatite in Zimbabwe, the Bancroft Belt of polymetallic pegmatites in Ontario, Canada, the uraniferous rossing pegmatites in Namibia, large pegmatitic lithium resources in Zaire and France, green bushes pegmatite, Western Australia, and large pegmatite belts in Mongolia. Pegmatites often classified as simple or complex. Simple pegmatites have simple mineralogy and no well-developed internal zoning, while complex pegmatites may have a complex mineralogy with many rare minerals, but their distinct feature is the arrangement of the constituent minerals in a zonal sequence from the contact inwards. Complex pegmatites display internal zoning that may be purely textural or purely mineralogical. Occasionally, zoning is a combined textural mineralogical feature. Complex pegmatites display coreward Younging feature. 5 hypotheses have been advanced to account for the development of internal zoning. Number 1, fractional crystallization under non-equilibrium conditions leading to a steady change in the composition of the melt with time. 2. Deposition along open channels from solutions of changing composition. 3. Two-stage model. A. Crystallization of simple pegmatite with B. Partial or complete replacement of the pegmatite as hot aqueous solutions pass through it. 4. Three-stage evolution during magmatic subsolidus hydrothermal evolution, beginning with a magmatic melt stage through an immiscible melt fluid stage, eventually to a dominantly fluid stage. And 5. Hybridization through assimilation of or reaction with country rocks. Most investigators prefer the first or the third hypothesis for the generation of pegmatites. It is possible that diverse mechanisms operate in their genesis, and at least in some instances, the elements are derived from the host rocks.